Hi, everybody. Welcome to this week's California Dreams Technical Series. We're glad you're able to join us, and we are glad to have as our speaker today Michael Gale from Sandia National Labs. Michael is a principal member of the technical staff with over 15 years of experience at Sandia. He has at least 29 publications and 13 patents in the field of quantum optics and integrated photonics. He's a lead researcher developing innovative integrated photonic devices and platforms for applications in RF signal process, cryogenic interconnects, quantum information, and sensing, all topics very relevant to California Dreams and the work we're doing here within the hub. His work is different than the technology that we are offering from Sandia in indium phosphide in MPWs from Moses 2.0, but still of direct interest to what we're doing here. Finally, Michael's the quantum photonics thrust lead on a large internally funded effort at Sandia, and we're looking forward to hearing about his interesting work here today. So take it away, Michael.
All right. Yeah, thank you. As Steve said, my name is Michael Gale. I'm a principal member of technical staff here at Sandia, and today I'm going to be telling you about, I guess, kind of giving you a very broad overview of some of the silicon photonics and heterogeneously integrated photonic work that we're doing at Sandia. I'm going to start out with a little bit of a history and background of Sandia and how we fit into things here at Sandia. Then go into an overview of some of the sort of specific photonic devices that we've been developing over the past decade or so, and then just finish by highlighting a few of the interesting projects that we've been involved in. This work is, a collection of work from many staff here at Sandia, but I'm happy to put you in contact with any of those staff if you have questions or want to follow up after this talk. You can reach out either to myself or my manager, Patrick Chu. So yeah, to give you some history of Sandia, our roots go back all the way to the Manhattan Project back in 1945 when Los Alamos created the Z division, which was in charge of developing the non-nuclear components and system integration. That officially became Sandia in 1945 when we became run by AT&T. The running of our lab was taken over by Martin Marietta in 1993, or sorry, 1993. Which then turned into Lockheed Martin in 1995, and then since 2017 we've been run by Honeywell. We are a federally funded research and development center. So for those of you that aren't familiar with that, that means we're government owned but contractor operated. So as I said, we're run by Honeywell currently, and the idea here is that we're a nonprofit organization, that we're not attempting to compete with industry, and that frees us up from a lot of conflict of interest and allows us to serve as trusted advisors to the government and also to help kind of facilitate interactions between government and industry. We have quite a few sites at Sandia, so you may be most familiar with our largest site, which is in Albuquerque, New Mexico, but we also have a pretty large size site in Livermore, California, and then a number of facilities and test sites across the country. The work at Sandia can broadly fall into 5 major program portfolios that we have. We have work in advanced science and technology, nuclear deterrence, global security, national security programs, and energy and homeland security. And most of what I'm going to be talking about today falls under this advanced science and technology portfolio, although we have programs that kind of span all of these portfolios. Within the advanced science and technology portfolio, it can be further broken down into a number of areas, but the work I'll be showing you is really mainly focused within our nano devices and microsystems portfolio. Within our microsystems capabilities, there's a number of facilities. The work I'll be talking about is primarily done at our MESA facility, the Microsystems Engineering Science and Application facility. But we also have efforts at the Counterfeit Detection Center, the Center for Integrated Nanotechnology, the Ion Beam Laboratory, and a number of unique radiation test facilities. And just to kind of quickly highlight, at the Center for Integrated Nanotechnology facility, this is a user facility. It's a collaboration between Los Alamos and Sandia. And as a user facility, external users can put in proposals. It's a pretty easy proposal process, about 2 pages. They have 2 calls every year. And if you're accepted, you can come to this facility and use the fabrication and experimental tools for free. So it's a great opportunity. If you haven't already, please check it out. And then within MESA, that's really kind of our main fabrication facility and where I do all of my work. We have a number of different facilities. If you look at the picture up here in the back left, this is our what we call our Sci-Fab, which is our 8-inch CMOS fabrication facility. The main mission of this facility is to provide trusted, strategically radiation-hardened CMOS electronics for NNSA. But I guess from my point of view, it's a really excellent facility that I get to use for developing these new photonic technologies. And doing a lot of interesting research alongside this production facility. And then immediately adjacent to that is our microfab facility, or our compound semiconductor fabrication facility. This is where we can do processing of materials that wouldn't normally be allowed into a CMOS facility. And so this is a really great capability. So we can do our CMOS processing in a highly controlled environment, and then take those wafers next door to this fabrication facility and do heterogeneous integration of 3,5 materials or lithium niobate or other materials. Within the MESA facility, there's a pretty significant photonics effort. We've got over 60 staff that are working in the area. And this is, again, spanning both our CMOS facility and our compound semiconductor fabrication facility, and then more interesting from my point of view is where we bring all of these together through either advanced packaging or heterogeneous integration to develop very interesting photonic microsystems. And so over the years, as a result of all of this effort, we've been recognized through a number of R&D 100 awards and quite a few high impact research journal publications. And we've also extensively collaborated with entities of all kinds, so universities, small and large businesses, and government alike. And we're always open to new collaborations, so please feel free to reach out if you're interested. With that, I'll go into some of the technical detail now. So just going back about over 15 years now, we began developing a silicon photonics platform at Sandia within the MESA facility. And through a variety of investment, both internal and external, we've been able to really mature that platform. It has a full suite of components, including low power, high bandwidth modulators and detectors, low loss optical waveguides. That could be either in silicon, or we've also got silicon nitride and aluminum oxide waveguides. We do selective germanium epitaxy for photodiodes. And as a result of the applications that we're interested in, we've done quite a bit of work to qualify these components both at cryogenics and in radiation environments. And as you'll see, we're interested in kind of the full range of applications, but just to mention a few, RF photonics, LIDAR, high bandwidth cryogenics and interconnects, and quantum networking and quantum computing. And so that's kind of our base platform, but we're continually trying to improve on the performance and integrate new materials and devices. And so a lot of the work we're doing lately has been on heterogeneous integration of new materials. You can see a cross section here of kind of what the full platform of heterogeneously integrated materials would look like. We've got aluminum nitride based devices for acousto-optics. We've got 3,5 indium phosphide based devices for lasers and amplifiers, flip chip integration of CMOS circuitry, and thin film lithium niobate for high speed electro-optic modulators. So just walking through our devices in a bit more detail, a lot of the work that we do is really dependent on having very low optical losses, and so we've invested quite a bit of effort in reducing optical losses, not just at telecom but across the full wavelength spectrum. So at telecom, we have your traditional silicon and silicon nitride waveguides, and we've demonstrated losses kind of on the 0.1, 0.2 dB per centimeter type scale. But then moving into the shorter wavelengths, it becomes much more challenging. For blue wavelengths, we've developed aluminum oxide waveguides. That's these red points right here. We've been able to demonstrate very low losses on the order of 1 to 2 dB per centimeter, going down even as low as 355 nanometer wavelengths. And then kind of an exciting result even more recently is that we've been able to develop a silicon nitride recipe that performs really excellent at blue and UV wavelengths. So we're seeing on the order of 0.6 dB per centimeter at 397 nanometer wavelength. And then the performance of that film just kind of improves as you go to longer wavelengths. So we're down into the kind of few dB per meter type losses at 780 and near infrared wavelengths. And then, just to mention, all of these wavelengths are tunable through either thermal or piezo tuning. On the bottom right here, I'm just showing an example of one of our thermal phase shifters where we can tune the silicon nitride Mach sender interferometer with very low power, only about 0.6 milliwatts required to get a pi phase shift. So then, building on these low loss waveguides, we've done quite a bit of work to integrate 3,5 materials for lasers and amplifiers. This is an example of our integration of O-band and C-band gain material on silicon waveguides. You can see on the bottom here an example of how we can span both the O and C band. These are, I guess, two different gain stacks, but then within that gain stack, we can tune the design just by changing the lithography of our silicon waveguide. And with this platform, we've been able to show around 20 milliwatts of power on chip, and amplifiers with about 30 milliwatts saturation power. Yeah, and yeah, if you're interested in more information on this, a lot of this work is the result of my colleague Ashok Kodagala. In addition to directly bonding the 3.5 material to our photonic chips, we've also done work with more of a hybrid integration approach where we edge couple the laser gain material to our PIC. And this is an example here showing 780 nanometer wavelength laser using our very low loss silicon nitride with we're able to achieve high Q ring resonators with quality factors on the order of 10 million. And we can then use that as feedback to the gain material to stabilize it and either tune the wavelength or reduce the laser line width. And so this example here I'm showing is using 2 rings in a vernier mirror type configuration where we've shown that we can get the laser line width down to about 20 kilohertz. And then if we instead do a self-injection locking technique, which is what I'm showing here, we've been able to show as low as about 100 hertz line width or a 1,000 times reduction in the line width of the free running laser. And then once we have lasers on chip, we need to provide some sort of optical isolation. And so we've also had work in acousto-optic isolators. So this work comes from my colleague Nils Otterstrom. This is a really cool device where he's used aluminum nitride to perform this acousto-optic mode conversion. The process requires phase matching, and so this device is set up so that light propagating in the forward direction does not meet the phase matching condition and simply propagates through the device without any alteration. On the other hand, light that gets reflected backwards does meet this phase matching condition and gets converted into a higher order mode, which can be rejected and provides isolation. He's been able to show 20 dB isolation with insertion losses on the order of kind of 2 dB and bandwidths on the order of 16 nanometers. So it's really kind of state-of-the-art type optical isolators. And then finally, we've been doing a lot of work on integration of electro-optic materials for high-speed, high-power modulators. This is an example here of how we've chosen to integrate thin film lithium niobate. There's a sort of a number of different techniques we've pursued. What I'm showing here is 2 examples where we, on the left here, we use our silicon waveguide. On the right, we have our silicon nitride waveguide. And in both cases, those are defined in our CMOS fabrication facility. And then in post-processing, we bond this thin film lithium niobate just above the waveguide. The optical mode overlaps with that electro-optic material. And so we're able to get an electro-optic response, but we don't have to do any sort of etching or post-processing of that lithium niobate, which is kind of notoriously hard to process. And then we can do electrodes for the modulator either on top of the lithium niobate in post-processing, or we can even just make the electrodes in our CMOS facility before we do the waveguides. And so in order to make this compatible with our full silicon photonics process, we've expanded on this idea a bit more, and you can see the process we use now highlighted on the bottom. We begin with a very thin baried oxide SOI material. We fabricate our silicon photonics as normal, but then we bond a new handle wafer onto the top of that, still at the full 8-inch wafer level. We flipped the entire thing over and removed the original handle. And so now our waveguide is at the top of the stack with a very, very smooth, pristine surface here. And we bond our thin film lithium niobate onto that. And this bonding we do at sort of the chip level. You can see here an image of one of these devices where we've bonded roughly a centimeter square piece of lithium niobate across an array of modulators here. And with this, we've shown bandwidths on the order of 70 gigahertz. And so we've qualified these devices at cryogenic temperatures as well. So this is an example of that chip being tested in a photonic cryogenic test setup. And in this case, what I'm showing on the right here is just an overlay of multiple optical spectrums where we applied an RF tone, looked at the sidebands from that modulation, and then stepped the RF frequency. And you can see the amplitude of those sidebands begins to fall off, mainly due to the cabling within the cryostat. But even with that fall off, we were still able to see operation out beyond 100 gigahertz with these devices, all at 4K. And then finally, more recently, we've been looking at pushing into shorter wavelength operation. So not only looking at lithium niobate, but also lithium tantalate, and really two motivations for this. One is the V pi tends to go down with proportional to wavelength, and then of course we want to be able to enable a number of quantum applications working with our ion trap and neutral atom groups here. And so this is an example of a recent device or chip we taped out where we've designed modulators working all the way from 493 out to 1762 nanometers on the same chip. And just as an example of how the V pi reduces at 729 nanometers, we're measuring a V pi of about 1.6 volts centimeter. And so to just kind of summarize, we've got a pretty wide range of devices that we've developed over the past 15 years or so. We're continually working to improve these, but just to give some examples, we've got integrated laser technology from near infrared out to telecom. We've got isolators that work at telecom with very low insertion loss and over very broad bandwidths. Our waveguides are functional from as low as 355 nanometer wavelength out to 2 microns with very low losses across that full range. We've got various different optical modulators. As I highlighted, we have thin film lithium niobate and lithium tantalate modulators, sort of your traditional silicon carrier depletion modulators, and then thermo, and I guess I forgot to mention it, thermo and piezo tuning of various devices. Using the same technology as our laser integration, we've also demonstrated amplifiers at C-band. We have a number of different nonlinear demonstrations using both silicon nitride and our integrated thin film lithium niobate. And then on the detection side of things, we have both germanium detectors for telecom wavelengths, and we've demonstrated silicon-based detectors for the shorter wavelengths. And so all of this, of course, is we would love to share with other people, and so we are more than happy to offer these devices through multi-project wafers. Our as a FFRDC, we're not attempting to compete with industry. And so, if you can get what you need from AIM Photonics or some other industry partner, then that's definitely what you should do. But if there's kind of unique devices, or if you want to make some custom changes to the fabrication or the process, then that's kind of where we excel. And so throughout the years, we've done multi-project wafer runs for a number of different collaborators and projects, and just highlighting a few examples here, things like beam steering chips for LIDAR and arrayed waveguide gratings. All right, and then I just wanted to then touch on a few different projects that we've got going on now or in the recent past. Beginning first with some of our big internal investments in photonics. So these two projects that I'm going to mention are both what we call grand challenges. So we have an internal R&D funding pool. It's called the Laboratory Directed Research and Development. And every year they fund one or two of these really large projects called a grand challenge. And so it's a 3-year effort to really kind of bring together multiple different groups within Sandia and tackle a really challenging project. And so we're really fortunate at the moment that our photonics group is involved in 2 of these efforts. The first one being this P-tree effort, which is a photonic-enabled terascale infrared imager. And the idea here is to develop new focal plane array technology to really push the state of the art, to increase the number of pixels and the frame rate of these focal plane arrays. And this is being done through a number of thrusts, including developing new detector materials, low power readout circuits, and then kind of the interesting part from my point of view is the optical portion, which is using integrated photonics for focal plane array backplane to read out all of this data that's being generated from this really large number of pixels and large frame rate. And then the second grand challenge that we're currently involved with is a quantum computing grand challenge. The name of that is EPIC, or Error Corrected Photonic Integrated Qubits. And the idea on this project is to develop a photonic quantum computing testbed for the government, and to build up the sort of the expertise of Sandia in the area of photonic quantum computing. We're pursuing sort of a unique approach to photonic quantum computing using frequency encoded qubits. So some of the more common approaches use spatial or polarization encoding, but we're looking to use the frequency of the photon to really make improvements in the scaling of this technology. So you can sort of using similar to WDM type techniques, we can encode many qubits on a single fiber or single spatial mode. And so this is a really interesting project. We've got a number of thrusts going all the way from the hardware, where we're developing integrated photonic photon pair sources, unique modulators to control the frequency of those photons, and then integrated superconducting nanowire single photon detectors. And then the project spans all the way, through the error correction and all the way up to the software level, where we're looking at really how to encode and control the qubits in this testbed. And then outside of these internal projects, we also have a number of external collaborations, and I just wanted to highlight those in case you're interested in how you might be able to collaborate with Sandia. And so there's a number of ways to do that. If we're able to collaborate with other federal agencies pretty directly through interagency agreements. For non-federal entities, there's a number of ways, including things like cooperative research and development agreements. You can also just come to us and license our technology directly. So we have a very broad patent portfolio in the area of photonics, with over 50 silicon photonic patents. Sorry, over 50 silicon photonic patents, 60 3.5 patents, and 20 metamaterial patents. Or if you're interested, you can just contract us directly through what we call a strategic partnership project, or SPP agreement, in which you would set up a contract with Sandia with a statement of work and deliverables. So to give you a few examples of external collaborations, this is one we had with a small company called Phase Sensitive Innovations and JPL. So this specific collaboration, we worked as a co-investigator. So we worked together with Phase Sensitive Innovations and JPL to develop the proposal and obtain the funding. And then we were funded directly from NASA through interagency agreement. And so this was a pretty exciting project where we were developing a RF photonic based radiometer. The goal was to develop this sensor that could be put onto a CubeSat to monitor the planetary boundary layer using this radiometer. And so under this project, Sandia, we not only provided the MPW service, but we also did a lot of the design and mask layout work. And so here's an example of that device that we fabricated for that project. It was an arrayed waveguide grating, which is basically just a very fancy filter. It takes a incoming optical signal and divides it into many spectral slices. In this case, we divided it into 51 channels, each with a 1 gigahertz bandwidth. And then the output of each of those channels goes to a germanium photodiode, so that it can be directly read out electronically and provide you with a real-time optical spectrum. And so this device we fabricated and then delivered to Phase Sensitive Innovations. They did quite a bit of impressive work to package this device and develop control electronics. And you can see kind of here the spectrum of the device. So at least one channel of the device being read out here. So they were able to demonstrate the operation of this very complex PIC. And there's more detail on this in this paper here, where which we just recently published, where we were able to combine this with a beamforming array and show that we could determine both angle of arrival and frequency of an incoming RF signal. As a second example, so this is more of a subcontract example of how we can collaborate. So a small company, Morton Photonics, that was recently bought out by Inflection. They had this idea of how to develop this linearized modulator, and they wanted to demonstrate a integrated version of that. So they subcontracted to Sandia to fabricate this device. And under this fabrication, or under this contract, we did new process development to develop some new methods to show active silicon photonic devices working with thin film lithium niobate. And again, we did a mask layout and fabrication, both the CMOS portion and the heterogeneous integration. And at the end of the project, delivered these optical modulator devices. And then just as a final example of a CRADA, or cooperative research and development agreement. This was a project from several years ago now, where we worked with a small company, Blackmore, who was bought out by Aurora. And for this project, we were interested in developing silicon photonic phased arrays for LIDAR. And so as a cooperative research and development agreement, we work very closely with the company to kind of lay out the device specifications and develop chips that could meet them. And so we did a lot of the optical design here, and then of course the mask layout, all of the fabrication, and in this case we also did packaging and testing. And ultimately we were able to demonstrate this optical phased array with it was roughly plus or minus 15 degrees of electrical steering and along one axis, and wavelength steering along the other axis. And so just to summarize, I guess we have a huge number of projects going on, so I can't go into a lot of details on all of them, but I just wanted to highlight kind of our areas of active research. So as I've mentioned, we're interested in RF photonics. We do a lot of work with arrayed waveguide gratings for RF channelization. We have work in LIDAR, as I showed just previously. We have a lot of work going on in high bandwidth density data communication, using things like our microdisc modulators, and this really ties into the P-tree project, where we're using these microdisc modulators to read out the data from a focal plane array. We have people here working in optical processing and data compression. And then more recently, we've got quite a bit of work going on in the area of quantum information. This was a project, actually another grand challenge project that we had, where we developed QKD transceivers within our silicon photonics platform. And in collaboration with MIT, we were able to demonstrate a fiber link with those transceivers. We're doing a lot of work at using photonics to scale quantum systems. So this is some work we're doing with our trapped ion group here, where we're integrating both low loss waveguides to deliver light to trapped ions, along with integrated detectors to read out the fluorescence signal from those ions. And in this specific case, the goal is to develop a very compact trapped ion atomic clock that could be used for precision navigation and timing. Similarly, in the area of quantum sensing, we've done work with our neutral atom group to develop PICs to deliver the needed laser wavelengths for atom interferometry. So this was recently published in Science Advances, where we use silicon photonic single sideband modulators to generate multiple different frequencies of light. Initially these are generated at 1560 nanometers, but then we frequency double those to 780 before being delivered to rubidium atoms, and we were able to show laser cooling and state readout of a cloud of cold rubidium atoms. And then last but not least, we have quite a bit of effort in metamaterials, including work developing really unique metamaterial design software, this Mirage software, which has been awarded 2 R&D 100 awards. And so to summarize, Sandia has a long history of developing silicon photonic devices going back over 15 years. We've got a really broad portfolio of components spanning the full wavelength range, and we're always interested in offering these to external partners through multi-project wafer runs. Many of these devices have been qualified at cryogenic temperatures and in radiation environments. As I showed, we're continuously trying to push the performance and develop new devices through heterogeneous integration. So we're currently integrating thin film lithium niobate and lithium tantalate, 3,5 materials for lasers and amplifiers, and continuously kind of pushing on the losses of our waveguides, moving to things like aluminum oxide and silicon nitride to get really low losses. And then, as I've mentioned, we're always interested in collaborating with external partners to kind of try to fill this gap between academic research and the high volume commercial foundries, and sort of this low volume but sort of unique or custom fabrication role. And so with that, I will conclude and open it for any questions.
Thank you very much, Michael. That was a great presentation. We already have 2 questions queued up in the Q&A session. The first I will ask on the anonymous attendees' behalf. Will the slides be made public? And Michael, I'll just offer, if you are willing to make them public, you can offer whether people can contact you, or we are happy to facilitate from California Dreams.
Sure. Yeah. If you want to contact me, I'd be happy to share them. Or I can also work with California Dreams to make them public.
Okay, sounds good. And then I'm going to offer to take David Chow off of mute. David is from HRL, and if he would I see it's already enabled. That's why I couldn't find it. Go ahead, David.
Okay. Michael, thank you for the presentation. I was interested in the vision for a very large format infrared focal plane array. I think you said more than 64 megapixels, which is obviously a lot and more than state of the art today. Do you envision, are you going to use some form of indium bump bonding like the industry does today, or do you have some other integration scheme to put that many detectors on a row?
That's a great question. Unfortunately, I am only loosely associated with the project. It's mainly being run by my colleague Christopher Long. So I'd be happy to put you in touch with him. I think he probably could answer it better than I could. So
thank you.
Okay, and we have another anonymous attendee question. Can you comment or connect me, and we'll have to figure out who me is, to the folks associated with quantum memory work, wondering what stage this effort is today?
Sure. Yeah. If we can find out who it is. So the quantum memory is, I guess there's a few aspects to that. I'm much more involved in this EPIC Grand Challenge, and my colleague Nils Otterstrom is kind of overseeing the memory aspect. We have currently we're using a free space type approach from a small company called PhotonQ. But we also are working on ways to develop an integrated approach, working with Peter Rakich at Yale. And the idea is essentially to integrate these extremely high quality factor cavities. So Peter has a really cool technique to develop ultra smooth, high reflectivity micromirrors. And through incorporating those with our integrated photonics, we can essentially form a cavity where we can modulate the coupling to catch and then release a single photon And yeah, by really pushing the Qs into the billions, we can store those photons for useful amounts of time.
Thank you. And if anonymous attendee wants to become unanonymous and get connected, please either follow up with Amy or Michael directly or drop your name in the chat or Q&A. And while we're waiting to see if there are any other questions, I don't see any other right now. I will just mention, since Michael has emphasized collaboration here, it just made me think I have been collaborating in different ways with different people, with Sandia for almost 30 years now. So apparently I started collaborating with Sandia when I was 5 years old. I have been glad to be working with them ever since and have always had good experiences. And we have 2 more questions. I don't know what order they came in, but I'll start with Nilesh.
I think Nilesh was just sharing their contact information for the quantum memory.
Thank you. Thank you, Amy. Nilesh, if you have any follow-up, you're welcome to come off mute, but otherwise we'll keep going on to Ben's question, and we can see if Ben can come off of mute to ask his question.
Okay, so the acoustic filters are notorious for having not so great extinction ratio, and none of the acoustic filter applications require better than 99.9% extinction, meaning that any leakage can become coherent crosstalk. So here you can filter things out, but what are the leakages that you get on an unwanted output?
Yeah, so I guess we're in this slide that I showed, we're using it for an optical isolator, and so I guess the extinction was on the reflected light was 28 dB. Yeah, I guess I'm not sure in terms of the extinction as like when it's used as a modulator. I would have to defer to Nils Otterstrom, my colleague.
All right, so that's the point I was asking you. In an isolator, you need to get better than minus 30 dB extinction. I mean, if you have a milliwatt, you need to maybe afford to have less than microwatt to go back to the laser.
Okay.
So I used to work on this acoustic filter before on lithium niobate, and that was one of the challenges we had.
Okay. Yeah, I think the yeah, and I could be misspeaking, but I think the contrast is probably limited by the mode conversion devices here. So essentially we're converting the reflected light into this higher order mode, and then we need to filter out that mode. And so I'm not sure. I think through additional design and improvement of the fabrication of those mode filters, we may be able to do better.
Right. It has to be amazingly uniform across that conversion. But that also brings another question. If depending on the frequency, if you have like a megahertz or 10 megahertz, your frequency will be shifted by that amount, correct?
Well, that's the nice thing about this approach is the forward propagating light is not shifted. It travels through this device totally unaltered, and then the reflected light is frequency shifted and also converted to this second order mode. But that's the light we're trying to get rid of. So we don't care if we frequency shift it.
Yeah, there's a trade-off. If you use the component that's not frequency shifted, then there's more crosstalk leakage. So there are trade-offs that you can. Yeah, I would like to see the paper. So that's the paper you have here. Okay, good. Thank you.
Mm-hmm.
Okay, and Alex from Keysight, we got your email address for the slides, so thank you for your interest in those. Amy took that down. We'll pause to see if there are any other questions. I don't have any in the queue right now. Going once. Going twice. Michael, we had a great turnout on what's a holiday weekend for some and spring break for some, so thanks bringing so much interest to our seminar today.
Mhm.
I will just also mention that we have seminars lined up for the next couple of weeks, including Dinesh Baradia from UCSD next week and John Lannon from Micros on April 17th. And then Amy, you can go to the next slide. We're still open for questions while we show these slides. Here's our QR code for registering to follow future seminars. And I'd also like to note that the number of YouTube views that we've gotten for these seminars is now over 10,000, which sounds pretty good to me. Probably there are thousands or many thousands of influencers who are way ahead of us, but I think in our area we're doing pretty well. Thanks to Michael for today's contribution for that, and I hope that we'll be able to put this up on YouTube and add to that tally. Otherwise, thanks to everybody and have a great weekend. And I assume we didn't go back to the technical side here for any last comment, or did we? I think it's just a screen sharing thing. So I think we're done. Thanks everybody. We'll see you next week.
Thank you.
Thank you.